So good morning. Let's get started, right? Okay. So yesterday, if you recall, we were looking at the state space representation, right? So we looked at how to rewrite a nth order ODE as a set of n first order ODEs, and the state space representation had two equations in general, right? What was called as a state equation, which is a first order vector ODE that provided the time evolution of the state variables, and then we had what is called as an output equation, right. So that related the system output to the state vector and the system input. Okay. So those were the two equations in the state space representation, and we essentially did an example where we rewrote the mass spring damper system governing equation in the state space form, right. And then we got an expression between the transfer function and the state space representation, which was this equation. P of s was C dot Si minus A inverse B plus D, and I left you with two homework exercise problems, right. So I asked you to first check the relationship for the mass spring damper system, and that's what I just worked out here. So this is the realization. So the matrix A, the vector B, and the vector C are these for the mass spring damper system. So these are quantities which you already derived yesterday. So if you just work it out, calculate Si minus A and then like Si minus A inverse. Of course, Si minus A inverse is going to be of course this multiplied by 1 by determinant of Si minus A, right. So that's the inverse. Okay. So that is going to be Si minus A inverse, and C dot Si minus A inverse B is going to be this, and if you do the algebra, you will see that you will get the transfer function itself. So just that's just an exercise to verify, you know, like, or check the formula that we derived for this particular example. Obviously it must be true, right. And then like I asked you to calculate the poles of the transfer function and the eigenvalues of the state matrix. So the poles of the transfer function are these. Okay. So these are the poles of the transfer function, minus C plus or minus square root of C squared minus 4mk divided by 2m, and we can see that the eigenvalues of the state matrix also turn out to be the same. Okay. So in fact, so to generalize, of course I am not telling the complete picture, but then like by and large, you know, like for what are called as minimal realizations, okay, the poles of the transfer function and the eigenvalues of the state matrix are the same. Okay. Of course, this is true for what are called as minimal realizations. Okay. So we will see what this is when we go to advanced courses on controls, you know, particularly on what is called as modern control theory or state space theory. Okay. Yes, please. How did I do that? How did I do, what do you want? Right. Okay. Okay. So first thing is that like you have Si minus A inverse to be a 2 by 2 matrix, first multiplied by the vector B, okay, which is a column vector 0 and 1 by m. So if you multiply that, you get this 1 by m and S by m, right. And then you have C, which is 1 0. You take the dot product with that, you will get 1 by m. See, what is the dot product of 1 by 1 0 and 1 by m S by m? You will get 1 by m. 1 by m, there is a m in the numerator, you get, m and m gets cancelled, right. You get 1 by m S squared plus C s plus k. Okay, so this is the determinant, right. See, what I have written here is the determinant, right. So of course, this is the reciprocal of the determinant. This is 1 by determinant of Si minus A, right. So what I have done is that like determinant of Si minus A is S squared plus C by ms plus km. This can be rewritten as just S squared plus, sorry, ms squared plus Cs plus k divided by m, right. So I am just taking m as LCM. So when you flip it, you will get m divided by ms squared plus cs plus k, and the m and 1 by m gets cancelled, so that's why you get 1 by ms squared plus cs plus k. Okay, simple algebra. Okay. So that I am not touching upon here. Okay. So essentially, as I mentioned, like this concept of the set of poles of the Planck transfer function being the same as eigenvalues of the state matrix is true if the realization is minimal. So what is a minimal realization? I preemptively give you the answer, but then like you will understand it better when you go to let us say modern control theory or an advanced course in controls that deals with state space. A minimal realization is one which is both completely controllable and completely observable. Okay. So then the question becomes, what is completely controllable and completely observable? So you will see that that's going to have a cascade effect. So we have to go deeper and deeper, right? So essentially, if you have a non-minimal realization, by and large, one would be a subset of the other. Okay, the two sets will be exactly the same when you have what is called as a minimal realization. So here you see that there are two poles of the transfer function and two eigenvalues of the state matrix, both are the same. So the set is the same, right? So that's something which we can observe. Okay, yeah, fine. So but why is this important? Because you will immediately see that the concept of stability, right? In fact, like we will learn what is called as stability about an equilibrium state when you go to state space based control. But then you can immediately feel that for a Bibo stability, we wanted all the poles to be in the left of complex plane, right? If you used a transfer function approach. So similarly, if I use the state space approach, right, for asymptotic stability, what should I have? I should have all the eigenvalues of the state matrix to be in the left of complex plane because the set is the same, right? So the task of ensuring asymptotic stability boils down to the location of the poles of the transfer function or the eigenvalues of the state matrix. Okay, so that's the equivalence which I wanted to show you here. Is it clear? What was the purpose, okay, behind this particular derivation, right? So of course we can go deeper and deeper, but I am not going to do that here because our course is mainly focused on transfer function based analysis. But I just wanted to give you an introduction to state space, and we would learn more about this in advanced course on controls, right? Okay. So let me now come back to our discussion using the transfer function. Okay. So we are going to discuss what is called as frequency response. Okay, that's going to be something which we are going to do for the next few classes, right? We are going to discuss what is called as frequency response and how that can be used for control design. Okay, so that's going to be the objective for this particular discussion, right? So till now, like if you recall what we have done, right? Predominantly, we have looked at the step response, right? So we have looked at the step response of dynamic systems to essentially come up with performance parameters like definitions like time constant, like rise time, settling time, peak overshoot, and so on, correct? So now we are going to analyze what happens when we provide a sinusoidal input to the system, okay? And that's what frequency response deals with, okay? So the term frequency response deals with the response of the system when a sinusoidal input is provided to it. Okay, so that's what we are going to look at. By and large, we are going to look at what to say the steady state response. Okay, we will see why. Okay, so what we will first consider is that, like, let us consider a stable. Okay, this is very important. Of course, we can only talk about performance only if we have a stable system to begin with, right? This is something which we already discussed, right? So, let us consider a stable LTI causal SISO dynamic system whose transfer function is P of S. Okay. So, let us say we consider a plant or a system with a transfer function P of S. So, what do we have? So, we have the system transfer function to be P of S. So, we provide an input u whose Laplace transform is u of s, and we get an output y. So, whose Laplace transform is y of s, right. So, immediately we know that y of s is going to be equal to P of s times u of s. Okay. So, let us consider u of t to be some u naught sin omega t. Okay. So, that is like we are considering a sinusoidal input. So, where u of t is some u naught sin omega t. Okay. So, the input has a frequency omega and a magnitude of u naught, right. And consequently, what is going to happen to the Laplace transform? So, we are going to get u of s to be equal to u naught omega divided by s squared plus omega square. Okay. So, that is what we are going to have, right, if I take the Laplace transform of this particular signal. Okay. U naught is the magnitude, all right. So, that is a constant positive real number, right. So, the frequency of the input is omega. So, that is what we are going to have for u of s, right. And so, let us say P of s be some n of s divided by d of s. Okay. So, this I can rewrite as n of s divided by, let us say, s plus p1, s plus p2, s plus pn. Okay. But and what do we know about all the poles of P of s? All poles of P of s lie in the left of complex plane, right. Why? Because we are assuming a stable system to begin with, right. So, all poles of P of s lie in the LHP, right. So, that is something which we already have presumed, right, in this particular discussion. Okay. So, let us now process this particular equation. So, this implies that y of s is equal to P of s times u of s. Okay. That is going to be equal to some n of s divided by d of s, okay, times u naught omega divided by s squared plus omega square, correct. So, that is something which we know. So, this I can rewrite as some a1 divided by s plus j omega plus a2 divided by s minus j omega plus some n1 of s divided by d of s. Okay. So, I am just doing partial fraction expansion, right. See, because what has happened, like, so the plant transfer function is n of s divided by d of s, then I multiply it with a second order term, denominator is s squared plus omega squared. So, what I am doing is that I am writing s squared plus omega squared as s plus j omega times s minus j omega, I can do that, right. So, essentially then we are doing partial fraction expansion. So, I will write for s plus j omega a1 by s plus j omega, and then s minus j omega, the residue I take it as a2. So, I get a2 by s minus j omega plus some n1 of s, whatever is left behind, divided by d of s. D of s is the original denominator polynomial, s plus p1 all the way till s plus pn. Okay. So, that is my output, right. So, and that is essentially this. Okay. So, this is nothing but, please note that this is P of s. Okay. Please remember that. Okay. So, if I want to find A1 and A2, what should I do now? Let us say I want to find A1. what should we do? We multiply both sides by s plus j omega, right. So, if I do this, what will I get? I will get P of s u naught omega divided by s minus j omega. That is what will happen to the left hand side. On the right hand side, I will get A1 A2 times s plus j omega divided by s minus j omega plus some n1 of s which is left behind, right, times s plus j omega divided by d of s, right. So, this is what I will get, right, if I multiply both sides by this one. So, now what should I do? I should substitute the root, right, of that factor, which is s equals minus j omega. I can do this. So, then what will I get? I will get P of minus j omega u naught omega divided by, what will happen to the denominator? It will be minus j omega, I will get minus 2j omega, and that is going to be equal to A1, right. Okay. So, this implies that the residue A1 is going to be equal to u naught divided by 2j, right, omega and omega cancel off, times P of minus j omega. Okay. So, what is P of minus j omega? P of minus j omega is the Planck transfer function evaluated at s equals minus j omega. Obviously, that is going to be a complex quantity, right. So, and we know that any complex variable has a magnitude and a phase, right. So, then there are various representations of a complex variable, right. I can have a representation in terms of real and complex part. I can have a magnitude and a phase representation also for the same complex variable, right. So, now what we do is then, if I have a complex variable P of j omega, I can rewrite this as the magnitude of P of j omega times e power j phi, where phi is the phase of P of j omega, right. This is one representation of a complex variable. Do you agree? Yeah. Yes. Yes, I missed it, minus. Thank you. You are right. Thank you. Okay. So, yeah. So, that is minus u naught by 2j P of minus j omega, right. So, I get this, right. So, this immediately implies that if I have P of minus j omega, what am I going to have? That is going to be P of j omega e power minus j phi. Okay. So, the phase just becomes negative of P of j omega, right. So, that is the representation which we are going to follow, right, for the complex valued function P of j omega. Okay. So, once I have this, what is going to happen to A1? This implies that A1 is going to be minus u naught divided by 2j, the magnitude of P of j omega e power j phi. Okay. Please remember what is phi? Phi is the phase of P of j omega. Obviously, phi depends on omega, right. You vary the frequency, obviously the phase also varies, right. So, that is what we have for A1. Okay. Now, similarly, let us figure out A2, right. So, let us get the expression for A2. So, if I want the expression for A2, what do? I multiply both sides by s minus j omega, right. So, this implies that I will get P of s u naught omega divided by s plus j omega, that is going to be equal to A1 plus A2, sorry, A1 s plus, sorry, what is going to happen? I multiply by s minus j omega, right. So, I will have A1 s minus j omega divided by s plus j omega plus A2 plus n1 of s minus j omega divided by d of s, right. So, that is what I will have, correct. I hope everyone agrees. Now, what should I do? Here I substitute s equals j omega, right? That is the root of this particular factor. So what will I immediately get? I will get P of j omega u naught omega divided by 2 j omega, that is going to be equal to A2, right. So omega and omega will immediately cancel. So A2 is going to be u naught by 2j P of j omega, then I just represent P of j omega as the magnitude of P of j omega e power j phi, right. So we are almost done, okay. So we are almost there, okay, just a few more steps. Okay. Now let us go back here, right. So our y of s is going to be a1 divided by s plus j omega plus a2 divided by s minus j omega plus n1 by d of s, right. So let me write it down. So our y of s is going to be a1 divided by s plus j omega plus a2 divided by s minus j omega plus n1 of s divided by some d of s. This immediately implies that if I take the inverse Laplace transform, what will I get? What will be the inverse Laplace transform? The first term I will get a1 e power minus j omega t, right, correct, and then I will get for the second term a2 e power j omega t, right. And what is going to happen to the next term, you know, like, so essentially let there be k distinct poles. This is something which we have already done, right, for an nth order system. Let us say let there be k distinct poles. The inverse Laplace transform of this term is going to be the following, right. So this is something which we have already done. So please go back and look at that. So let us say let there be k distinct poles with mu I being the multiplicity of each pole. We have already figured out what is the inverse Laplace transform, right. So this is what we will have, right. So the main thing is that like we are going to have the poles as the exponents, right. So this is something, if you recall, which we did when we analyzed stability, if you recall, and this is the result where we used to figure out that if my poles lie in the left of complex plane, the system is going to be Bibo stable, right. So if you recall, that is what we did some classes back. So essentially I am just going to get the same structure, right. So that is very important as far as this is concerned.